This video is about double integral in polar coordinates. First of all, let's review what is a polar coordinate. On the xy plane, for giving any point, you can write in either rectangular coordinates xy, this distance is x, this is your y. Okay. Also, you can describe same point by its polar coordinates, which is r and theta. Okay. What is r? R is the distance from the origin to this point, and the theta is this angle. If I look at this graph, obviously x is equal to r cosine theta, right? And y is r sine theta. It's easy to see that. Okay. So given r and theta, we can convert polar coordinates to rectangular coordinates, vice versa. Alright, now let's see what is a double integral in polar coordinates. First of all, I want you to understand the purpose of this section is also like a previous one, is to calculate double integral. So let's recall what is a double integral again. So you have a domain on the xy plane. And you have a surface z equal to fxy. Okay, now we want to, what is the double integral? Double integral is to find the volume under this surface. So what do? We only know how to find volume for rectangular box, right? So obviously this is not a rectangular box. So what we did is divided this domain to many rectangles. Okay, so this is a typical one. This area we call dA. Okay, so give x, y here any point. This point, this height is fxy. So if you look at this one, you got if your dA is small enough, then this volume you can consider as rectangular box. So fxy times dA will give you this volume for this rectangular box. Then add them together, take a limit. That's exactly what its integral means. Okay, so this is definition for double integral. Now the question is, how do we calculate that? And we learned in the previous section, we learned this double integral can be written as two iterated integral. One is, see this area, this distance, this length is dx, and this one is restricted to y. This is the dy. Okay, so this area dA is a rectangle, can be written either dx dy or dy dx. So that's why we can write this as a two iterated integral, dx dy or dy dx. Then you fill up those signs corresponding to different domain d there. Okay, the purpose of this section is, again, we want to find this double integral. If your region d there, if your domain d there is in some shape like this, for example, this is my d. Okay, if shape like that, for some domain and also for some function fxy, it's easier to write, to express them in polar coordinates. Okay. So we'll explore the third option to find a double integral other than dx, dy, dx. Okay. If this is our region D, okay, now we want using polar coordinates. So what we did is, again, we just like what we did before, we divide this region to many small areas, and then we can replace the volume on the surface by rectangular box volume. Okay. So remember this direction is your R. So this this is our dA, okay? dA. This dA can be written as a dr, then times this length. Now this is what we call this difference is d theta. Okay. However, this arc length is not d theta. It's r times. Okay, from here to here. This is our r. Okay. Let me put this way again. Okay. This is a part of a circle. Okay. Here is a theta. Here is r. This arc length is r times theta. Okay. Therefore, this length is r d theta. So this dA, this area, can be written as r dr d theta. Okay. Therefore, this double integral, right in terms of polar coordinates, can be written like this. Okay, first of all, x, remember, x equal to r cosine theta. Your y is r sine theta. Then replace your dA by r dr d theta. I want to emphasize here, this r here is not part of the integral, not part of the function we try to integrate. Its goal is dA, okay? It's always there. Doesn't matter what is your fx. Y, okay. Okay, now, then we'll have to fix these four limits for the integral. How do we fix those? Let me give you, okay. Keep this picture in your mind, okay? Now, x, y. d theta go outside, okay? Always look at what is the restriction for d theta. For theta, look at any point here. Say this angle is alpha, okay? And this big angle is beta. For any angle, for any point here, they have their coordinates r theta, okay? Obviously, your theta here, this is your theta. Your theta will be bigger than alpha and less than beta. Okay, then you fix your theta. This is the theta. For given theta, your r to be in this region, your r must be bigger than this point and less than that point, right? And all those points are there in the region. Okay. So what is that point? This point is on the curve. For the different theta, this r will be different. So normally this is a curve, say r. I call this curve, okay? Is r equal to g1 theta. And this curve is r equal to g2 theta. For given theta, you can find r. Okay. Therefore, you have g1 theta and g2 theta. Okay. Keep this picture. Okay. Keep this picture in your mind. Okay. Then it will be easier for you to find what is those four limits, which is important. Okay. Okay. Now let's look at the example. How we. So okay, let me say that again. What is the double integral in polar coordinates? Just like the previous two iterated integral, this is just a third option for you to calculate double integral. Okay. Our purpose is still to calculate the double integral. So now we'll have three options double integral can be written as 3 iterated integrals. For the different situations, one is easier than the others. Okay, now let's look at let's see, we know, for example, I give you a circle. Radius is a. Okay, what's the area? We know the area is what? Pi a squared. Okay, do you ever ask yourself, how do we get this pi a squared? Okay, now let's find out. Okay, first of all, let me ask you a question. For given domain D here, right here, I give you domain D here, okay, x and y. Okay. What this double integral means? This one, you said I don't see any fxy there. That means what? That means the function we'll have there is a 1. Okay. So what kind of function is that? Okay, this is our D. Okay. Remember, double integral give you the area volume under the surface. So what is the volume here? What is the surface here? The surface is a what? 1. Okay. That means your fx y equal to 1. You can write this way, z equal to 1. What is z equal to 1? Z equal to 1 is a plane, right? Is a plane parallel with xy plane. Just like that. Okay. So the volume under this surface, on this plane, this is a cylinder, right? Because my plane is a special one, z equal to 1. So this volume can be found out by what? Base area of D times the height, right? This, because the height everywhere is the same, so just times 1, okay, which give you the area of D. Okay, what that means? That means this is a double integral. If you don't see anything there, that means 1 is there. Your surface is z equal to 1. Give you the area of your domain. Okay, now let's use this formula to find the area of the circle. Let me draw that here. Again, x and y. My domain here this time, okay, this is the example. Okay. My domain is this circle, okay, with radius a. Okay. Okay, now we know this double integral give you the area of the circle of your domain, which is a circle. Okay. So how do we find the double integral? You can use 3 iterated integrals: dx, dy, dy, dx, or r, dr, d theta. Okay. So this is a circle. Obviously, it's easier to use the polar coordinates. Okay. Okay. Now let me write different way. Okay. For example, we want to write in this way, dy dx. Okay. If I want to do this way, how do we fill up those 4 things? So dy dx, first see what is the smallest x, find the smallest x and the largest x. Obviously it's from negative a to positive a. Then make a projection on the x-axis. That's what we'll get it. Minus a, positive a. Okay. Then you fix x in between. This odd y here, odd point here in the region. So your y must be bigger for giving x. Your y is bigger than this point, less than that point. So to find those points, we need to know the formula for this curve and the formula for that curve. Okay. This is a circle, okay, which is the formula x squared plus y squared equal to a squared. You solve the y, you got positive or negative square roots a squared minus x squared. Okay. So if you take a negative sign, you got the formula for this bottom curve, y equal to minus square root of a squared minus x squared, and this one give you y equal to square roots a squared minus x squared. So you have this x squared a squared minus x squared positive square roots a squared minus x squared. Okay. Obviously this one you can integrate that, okay, but it's not easy to do. Okay, now let's use the polar coordinates. Polar coordinates, we have 1 here, so you still have 1. If you see, what is the polar coordinate? Whenever you see x replaced by r cosine theta, okay, we don't have x there, so then we change dA by r dr d theta. Okay. Now let's fix those things. Okay, this obviously for all the point, for example, point here, you have theta equal to 0, right? Point here, theta equal to positive. So all around, you have theta. Theta can be anything, so it's from 0 to 2 pi. Then you fix theta in between. You go there. Your r there is bigger than, see, all the r is there. Bigger than 0, less than that point. Okay. What is that point? That point is on the circle, right? Formula for the circle is x squared plus y squared equal to a squared. Replace x by r cosine theta. Replace y by r sine theta. So you got this. R squared sine squared theta equal to a squared. Using the identity cosine squared theta plus sine squared theta give you 1. So you simplify that, you got r equal to a. See, this is circle. Write the formula for circle, write it in rectangular coordinates. That's the formula. For polar coordinates, you got a simple one. Okay. So your r is from 0 to a. Okay, integrate this. 0 to 2 pi. Integrate about r, give you 1/2 r squared from 0 to a d theta. Replace r by a, give you 1/2 a squared minus replace r by 0. That's it. Okay. A is a constant. Okay, so you got 1/2 a squared. Integrate that, give you theta. Evaluate 0 and 2 pi. Okay. So give you pi a squared. Okay. If you want application for the calculus, this is the one. Okay. All right. Now let's look at another example. This example, we want to convert iterated integral, giving iterated integral to a polar coordinates. This is the iterated integral we have. Y here, dx dy. Okay. As we know, this iterated integral must be related with some double integral. I mean, function is x squared y dA. Okay. And this double integral can be written as another two iterated integral. Okay. Okay, so to convert this one to a polar coordinates, we have to figure out what is the region D by giving 0a and the negative square roots of a squared minus y squared 0. We need to figure out what is the D by giving information. Okay. Let's see what is region D. Okay, this one is dy go outside. your y is between 0 and a. Okay. Your y is between 0 and a. Here is a. Okay. So anything in this strip, they have their y coordinates between 0 and a, right? Okay, now let's see what is the restriction for x. Okay, they said that x is bigger than this bottom one. So your bottom curve is x equal to minus square root a squared minus y squared. Okay. If you don't know what this curve is, square that, which give you x squared plus y squared equal to a squared. So this one really is a part of a circle. Okay. Since x is negative, they give you this part of a circle. Okay. And this is your bottom curve. What is the top curve? Top curve is 0. You say, what is 0? It's really is x equal to 0. Okay. It's a y-axis. It's like here. Okay. So this is your bottom curve. This is your top curve. And y is between 0 and a. So this is your d. Okay. So once we know what the d looks like, then we can write this one. And we know this one is a double integral. Okay. And we know double integral can be calculated by polar coordinates. By the right like this. Okay. Now you have replaced x by r cosine theta. So square this. Then replace y by r sine theta. Change your dA by r dr d theta. Okay. Okay, now the question is, okay, the word is always dr d theta. Okay, first of all, let's see what's the restriction for theta. For example, my theta is 0. Here, all the point here, theta equals 0. So theta is 0. It's for all the points theta equals 0. It's not in your region D there, right? Theta is here 45 degree. You don't have points. So until your theta is what? Bigger than pi over 2, right? This here theta equal to pi over 2. You have some point in the shaded region. Okay. So theta is bigger than pi over 2. Then keep increasing until you get here, which is a pi. Okay. Okay. So see, all the points in the second quadrant, there is a theta between pi over 2 and pi. Okay. Then you fix theta arbitrarily in between this region. See what's the restriction for r. R is bigger than 0, right? And less than this point. What is that point? That's a circle. We just said that before. The formula for the circle is what? R equal to the radius. What is radius here? A, right? So it's 0 to a. Now let's integrate this one. This is much easier to integrate than original iterated integral. Okay, this is the integral about r. Theta is constant, so you got cosine squared theta, sine theta. They're all constant. You really need to integrate this. R to the square, another 2/4 dr, then d theta. Cosine squared theta, sine theta. Integrate this, give you 1/5 r to the 5, 0 to a, d theta. Cosine squared theta sine theta. Replace r by a, give you 1/5 a to the 5th. A is a constant. Okay, then replace r by 0, you got a 0. Okay, how do we integrate this? This is a constant. Take that out. Cosine squared theta, sine theta, d theta. Okay. How do we integrate this? Remember, we use variable substitution. Let u equal to cosine theta. Then your du equal to minus sine theta, d theta. Okay, then this ends become to cosine theta is u, so you got a u squared. Okay, this ends give you u squared. Then sine theta d theta. Sine theta d theta give you negative. I put negative here, okay? Otherwise you confuse at the minus. Then du. Okay, you can change those two things. Theta is between pi over 2 to pi. When theta equal to pi over 2, your u equal to 0. When theta equal to pi, your u is what? Minus 1, right? So you got minus 1/5 a to the 5th, and times 1/3 u to the 3rd, evaluate 0, and then minus 1. You got what you want.